In this video, we're going to have a look at Prim's algorithm, which is a method for finding minimal weight spanning trees of undirected graphs. In order to understand what that means, we're going to use a simple example here. Imagine we have four cities, 1, 2, 3, and 4, and we want to connect these four cities with roads so that we can get from one city to any other city that we want to. So we ask a construction company for a quote about how much it would cost to build some roads, and they give us this information back. We could build these roads, for instance, road from City 1 to City 2 for $100 million. We could build a road from City 1 to City 3 for $50 million, 3 to 2 for $120 million, 3 to 4 for $10 million, or 4 to 2 for $5 million. These are our options. We haven't built any of these roads yet. And our challenge is to decide which of these roads we should build in order to spend the least amount of money altogether and yet still be able to connect all of our cities. So we may not need all 1, 2, 3, 4, 5 roads. As a matter of fact, at the end of the day, we're only going to need 3. So Prim's algorithm is a way of deciding which roads we should choose to build. So how does Prim's algorithm work? Well, first of all, we choose a city to start with that we kind of get for free. In this case, we'll choose city number 1. So I mark city number 1 green here, which indicates that we can access city number 1, like we start in city number 1. And from there, Prim's algorithm is a greedy algorithm, which means that it makes the best choice, the most greedy choice available at any given stage of the algorithm. Now, in this case, greedy means we want to spend as little money as possible. So from city 1, we could either build a road to city number 2 or a road to city number 3, and we choose to do the greedy thing, which is to build the road to city number 3 for only $50 million because it's cheaper. And then we ask ourselves, from anywhere in the set of currently accessible cities, and the set of currently accessible cities is 1 and 3, what is the cheapest road that we can build to a new city? So from city 1, we could build over to city 2 for $100 million. And from city 3, we could build over to city 2 for $120 million. That doesn't help us. Or from city 3 over to city 4 for $10 million. And city 3 to city 4 is the cheapest road that we can build from the set of currently accessible cities to a non-accessible city, a city that we haven't gotten to yet. So we choose to build this one. Now from here, clearly our last city we're going to build to is city number 2. What's the cheapest way that we can do that? Not this one, but the road from 4 to 2. So that's the road we build. And it turns out we didn't need these two expensive roads at the end of the day, the $100 and $120 million roads, so we're going to take them off. And what remains is the set of roads that we need to build in order to connect our cities for the least amount of money possible. What we call the minimal weight spanning tree for our graph of cities and possible roads that we could have built. All right, so why do we call it a minimal weight spanning tree? Well, in graph theory, the cities would correspond to vertices, and the roads that we build between the cities are called edges. The weight of each edge is the cost to build that road, essentially. So we have chosen to build these 3 roads, which is a minimal cost set, and therefore we call it minimal weight in the language of graph theory. Furthermore, our roads need to connect all of our different cities. That is, our set of roads needs to span all of the different vertices in our graph. Our set of edges needs to span all of the vertices. So this set of 3 edges is a minimal weight spanning set. Okay, but now why do I call it a minimal weight spanning tree specifically? And I call it that because the process by which I chose sequential cities to build to can be thought of as kind of a family tree. I started with great-grandma, city number 1. And then from city number 1, I built to city number 3. That is, city number 3 is a child of city number 1 in our family tree. And then from city number 3, I built to city number 4. So city number 4 is a child of city number 3 in our family tree, or conversely, city number 3 is 4's parent. And then from 4 I built to 2, so 2 is a child of 4 in our family tree. Now this isn't maybe a typical family tree that you would see in a genealogy, for instance, because we only have one child for each parent, right? And also it only takes one parent to make a child. It's like asexual reproduction or something, right? So in that way, it's kind of not typical of an actual genealogical tree, but we get the idea. And it is possible, if we were to start maybe at a different vertex, to produce a situation in which each vertex has more than one child, unlike this particular case. So what would that look like? Well, it turns out that we can do it just by using the same starting graph, but beginning at vertex, say, 4 instead of vertex 1. So if we assume that we have vertex 4 for free, and we start there, we ask ourselves, what's the cheapest road that we can build out of vertex 4? And the answer is, it's this road over to vertex 2, which means that 2 is going to be a child of vertex 4 in our family tree eventually. And then we ask, from vertex 4 or vertex 2, from our set of currently accessible vertices, or currently accessible cities, what's the cheapest road that we can build to a new city? Well, from vertex 2, we could build this $100 million road, we could build this $120 million road, or we could build this $10 million road, and the $10 million road is cheapest, so we choose to do that. Which means that city number 3 is a child of city number 4 in our family tree. Okay. From here we ask, what's the cheapest, from any of these 3 cities, what's the cheapest road that we could build to a new city that we haven't accessed yet? And of course that city is going to be city number 1. This road ain't the cheapest. This road is our cheapest option, so we choose to build that. Which means that city 1 is going to be a child of city tree and our family tree. And so we build our city tree again as follows. We started with vertex 4. Vertex 2 was its first child. Vertex 3 was its second child. And then vertex 3 had a child, which was city number 1. And so we have now here a slightly more normal looking family tree where we have a parent who has a couple of different children instead of just one. Okay. So that's why we call it a minimal weight spanning tree, and that's the basics of how the algorithm works. But now how do we actually do it with code? So in order to do it with code, we're going to need some variables that are associated with each vertex. The first variable we are going to deal with is called parent, and there is a parent for every single vertex. Unsurprisingly, it's going to be related to this family tree we were just talking about. So what does parent represent? Let's choose a particular vertex here, vertex 3. Parent 3 is the city with the cheapest road to city 3 that we've seen so far. Now that doesn't necessarily mean that at every stage of the algorithm, the parent of city, once we set parent of city 3 for the first time, that is set in stone and it's going to end up being the parent in the final family tree that we come up with. No, that's not the case. It's just the city with the cheapest road to city 3 that we've seen so far. That is, it's sort of the front runner to be the parent in the final tree, but it might not end up being the parent in the final tree. That is until we decide to actually build a road to city 3. Okay, and then we have this variable distance. The distance for city 3 is the cost of the cheapest access road to city 3 that we have seen so far. So for instance, this distance might be like 50 for $50 million if the cheapest way of getting to city 3 that we have seen so far is from city 1. In that case, parent of 3 would be 1, and distance of 3 would be 50 for $50 million. And then we have this variable in tree here, and in tree is true for city 3 if city 3 is in the tree of accessible cities, i.e. the cities we have already connected with roads. Another way of thinking about that is just the cities that I've marked green in my earlier quick explanation of how the algorithms work. So in tree will be true if the city has been marked green, and we can access it from other cities. Okay, and then we have this global variable over here that is not associated with each individual city but is off by itself. What does this variable v do? V is one of two different things because there are two different kind of stages, two different sort of phases of our algorithm. In one phase of our algorithm, we have just built a road to a new city, and we are considering new options from there. We are considering the roads out from that city to new and undiscovered cities. So in this phase of the algorithm, V is the city that was made accessible most recently. Or to put it differently, it's the city whose edges or whose out roads we are currently exploring during that phase of the algorithm. Now, after we've explored all the roads out from the most recently added city, then we move into a phase where we're deciding which city we should actually build to next out of all of our options, including not only the roads from the city that we were just looking at, but any other roads from other cities in the set of accessible cities. So when we move into that phase of the algorithm, V is going to represent for us the current winner for the next city to build a road to, that we will build a road to. So that is the next cheapest city that we can get to, basically. Okay. And so those are what our basic variables mean. We will have a couple more of them later in the algorithm that I will introduce, and we'll explain those when we get to them. Okay. So then, what does it mean, and what should be our initial values for our variables? Well, parent for each of our vertices or each of our cities is initially set to -1, which isn't any of our cities, right? It should be one of our cities, but it's not, which means that we haven't yet seen any access roads to that particular city yet. So if parent of 3, for instance, equals -1, that means we haven't seen any access roads to city 3 yet at all. And likewise for all the other cities, which makes sense at the beginning of our algorithm. We haven't started exploring any roads, so there is no parent for any road. We initialize the distance variable to be max, or max integer, which is kind of like infinity. Distance 3 equals max means that city 3 is maximally or infinitely costly to access because we have not yet seen any roads to city 3, right? So they're like, no, at the beginning of the algorithm, there's no way we could get to city 3. It would be infinitely costly to get there. It's just not possible. So we set the distance or the minimum cost to be kind of infinity to get to city 3. And then at the beginning of the algorithm, none of our vertices are yet in the tree of accessible cities. None of our cities are connected with roads yet. So we say that in tree is false. And again, in tree is false for city 3 means that city 3 is not yet in the set of accessible cities. We have not built a road to city 3 yet. Okay. So now we're going to begin our algorithm. And we start by choosing a vertex for free. So here we're going to choose vertex 1. We assume we can access this vertex without any roads. But we don't actually need to choose vertex 1. We could choose any vertex that we want for our start, just like we did in our quick overview at the beginning. So now we're going to work out the details starting from vertex 1. And in order to do that, we're going to use Stephen Skiena's implementation from the Algorithm Design Manual. Which looks a little bit like this. We're skipping over some initialization stuff that we did on the previous page here, but we set V equal to our starting vertex, and we set the distance to that start to be 0, because in the distance from the set of sort of the minimum cost to get from the set of currently accessible vertices to the starting vertex is 0. We don't have to build any roads to get from vertex 1 or city number 1 to itself, right? So the cost of getting to vertex 1 from itself is 0, and we say that vertex 1 is now in the tree of accessible vertices. Okay, what do we do next? Well, we have this while loop here in the code, which is going to take us through all of our different cities, is the idea. It's going to take us through all of our different cities one at a time. And V is going to have a different value every time we execute this while loop. So While in tree for v equals false, we set in tree for v to equal true, and I kind of already did that step here. I set in tree for vertex 1 to equal true. And then I do a little bit of pointer work here. I'm going to skip over the details of this, but basically P is an edge coming out of our current city whose edges we are exploring, V. So P is going to be an edge that's coming out of city 1. Like, for instance, this edge pointing over to city 2. Now, the variable w is set equal to p dot y, and again, that is dependent on Skiena's implementation. You can look earlier in his book and at his implementation of edge node objects to see exactly how this works. But basically, w is going to be the city to which our edge points. So that is, in this case, our edge is pointing to city number 2. And weight is going to be the weight of the edge under consideration. In this case, weight will be 100. So then we have this if block here, and the condition for our if block is, first of all, that in tree for the city to which our edge points must be false if we're going to do anything with this edge. And we check and see it, and yes, city 2 has in tree equals f for false. Which means that it's not yet in the set of accessible cities. The other condition for this if block is that the weight, which again is the weight of the current edge, must be less than the distance for the city to which that edge points. Okay, and what does distance mean again? Well, remember, distance means the cheapest cost that we have seen so far for accessing this particular city. Now, the cheapest costs that we have seen so far for accessing city 2 is kind of infinity, because up until we hit this edge, we haven't seen any ways of getting to city number 2. So, if this weight is less than this cost, then this edge provides us with the cheapest access to this city. So, what should we do in that case? We should set the distance for that city to be equal to that weight, and set the parent for that city to be the origin of this particular road. That is, we set the distance to be 100 and the parent to be 1, because again, the cheapest cost that we have seen so far for getting to city number 2 is $100 million, and we would get there by traversing this particular road from city number 1, or building this road from city number 1. Now, we haven't choose to build the road yet. So the parent is kind of the current winner, but it may not be the actual parent of city number 2 in the final family tree at the end of the day, the final minimum weight spanning tree that we get to. It's just that parent 1 is currently in the lead for best means of accessing city 2. Okay, so now we set p equal to p next, which is traversing the adjacency list of vertex number 1 officially. But what that really means is we just go on to the next edge that's coming out of city number 1. So we go on to the next edge and we continue with this little interior while loop here. And now w is going to be city number 3, we're going to be looking at this edge, and weight is going to be 50. So we ask ourselves, is in tree for city number 3 equal to false? And the answer is yes, it is. And is the weight for for the edge we are currently considering less than the distance of city 3? And 50 is in fact less than max, or like infinity. And again, because this number is less than this number, that means that this road provides us with the cheapest access to city number 3. So we note that and say that the cheapest access we've seen to city number 3 would cost us $50 million, and that would be coming from city number 1, its parent. That's, again, these two lines of code in here. We set p equal to p dot next, which takes us to the next edge coming out of vertex number 1, or the next road coming out of city number 1. But there are no more roads coming out of city number 1. You'll notice we covered both of them. So this little interior while loop here terminates, and we move on to the next sort of phase of our algorithm, which is going over all the cities that we have available so far and finding the one that gives us the cheapest access, and that's the one we're going to build to next. So how do we do that? Well, we move on to our second meaning of v. We say v equals 1. Now v happened to be 1 already, and we set distance equal to max int, or excuse me, dist, which is different than the individual distance variables associated with each city. Now, what do these things mean at this point? Well, we already briefly talked about what v equals 1 means in the second phase of the algorithm now. It means the city that is kind of currently in the lead for next city to build a road to. We're going to look through all the different cities here and find the one that's cheapest to build to that's not already accessible. And we blindly choose that v equals 1 to start with. That's going to change as we go through all of our vertices, but we sort of make this blind choice. And then we also have this dist variable. What is this? The dist variable is going to keep track for us as we iterate through of all the cities, which one is currently the cheapest one we have seen to build to next. Or rather, I should say, it is going to keep track of the cheapest road that we can build that we have seen to get to a new city. That is a city that's not already in the set of accessible cities. So again, the cheapest road that we can build to get to a new city is going to be dist. Okay, so as of right now, before we start going through all the vertices, we haven't seen any new cities that we can build to at all. So it's not possible for us to build a road to a new city until we found one. And so we have dist equals max. Okay. So then we begin this for loop here, which is going to iterate for I equals 1 up to the number of vertices in the graph, or that is the total number of cities, which is going to be 4. We are going to do the following if block. So we start with I equals 1, which means we're kind of pointing at the first city here. And then we check out this if block. We ask ourselves, first of all, is in tree for the current city equal to false, the one that we are pointing to with the yellow pointer? And the answer is no, because for city 1, it's already in the tree, right? So we don't even have to consider the second part of this, this if condition here. We know that this if block is not going to execute, and we move right on to the next vertex, which is I equals 2. And now our yellow pointer is pointing to city number 2 here. And then we ask, okay, is in tree for city number 2 equal to false? And the answer is yes, it is. This is not yet in the tree. So then we look at the other part of the condition for this if block. Is it true that the distance for city 2 is less than the dist variable, which again is the lowest cost that we have seen so far for getting to a new city of all the cities we've iterated through. Now, that is this less than this? And the answer is yes, this is less than this. And so we should say that the cheapest city, or rather the cheapest road that we have seen so far that you can build to get to a new city costs $100 million. So we set dist equal to 100. And that cheapest city to build to is city number 2. And so we set v equals 2. And again, I am indicating the current next best option to build to with this kind of bolded outline here. Okay, so currently 2 is the winner for the next for the best city to build to next. But we haven't finished iterating through our vertices. We've just done 1 and 2 here. So we now continue this if block. Oh, by the way, I did set dist equal to distance for 2, and I did set v equal to I. That was here and here. So now this if block finishes, and I move on to the next iteration in the for loop. I now increases to 3. My pointer is pointing to our city number 3 here. I ask, is it in the tree already? It's not, so that part's okay. And is the distance for city number 3, that is the cheapest cost road that I can use to access city 3, is that less than the cheapest cost road that I've seen altogether so far to get to any new city? And the answer is yes, because I can get to this city for $50 million, and the cheapest city that the cheapest access I had seen previously was to city number 2 for $100 million. So I now replace the cheapest access overall, this dist variable, with 50, and I replace v with 3. City 3 is now winning for best city to build to next. Okay, and then I finish the for loop. After this if block finishes, I move on to the final iteration, which is I equals 4. And we have, does entry equal false? Yes, it does, so entry equals false. And then we ask, is the distance for vertex 4 less than the current minimum distance that we have seen so far? And the answer is no, it's not. We haven't seen any way of getting to city number 4 yet at all. So city 4 is not a better option for building to, definitely not, than city number 3, and we do not update these variables, which now means that our whole for loop here has finished, and we are ready to go on to the next iteration of the while loop with our winner, city number 3, as our next v, from which we will check outroads and so forth. Okay, so we have our winner is 3. We enter this while loop. We set in_tree for city 3 to be true, which means functionally that we decided to build this road to city 3, although in the code I never actually mark this road as having been built. So I'm not going to mark this, I'm not going to color code this road as being like purple to indicate that it's been built, because it turns out that I'm using other variables in the code to keep track of the sequence of roads that I build. Namely, I'm using this parent variable for each vertex to keep track of like which roads I built when. So I don't have to mark this, but it sort of does mean that I did build, I chose to build this road. All right, so now I'm going to process all the edges from city number 3. Again, P equals the first edge that's coming out of city number 3, so P is going to be this this road that actually happens to go back to city number 1, right? The first road out of city number 3 takes us right back to city number 1. We look at this condition in the if block and we say if in_tree for W, and remember W is the city to which our edge points, in this case city number 1, is equal to false. We're going to maybe do this if block, but city number 1 is already in the tree. That's true, so we skip right over this if block and go on to the next edge that's coming out of city number 3, the next road that's coming out of city number 3, which is this $120 million road over to city number 2. Okay, so then we ask, is city number 2 already in the tree? And the answer is no, in_tree is false for city number 2. So so we're good on that first condition of the if statement. And then we also ask, is the weight for the edge that we're currently considering, 120, less than the distance for city number 2? And is 120 less than 100? And the answer is no, it's not. That is, there's already a cheaper way of getting to city number 2, and that's from city number 1. So we don't have to worry about this, this road right here. We don't reset any of these variables. This road's going to be useless to us. We jump right over these two statements in the if block, and we set p equal to p arrow next, which means that we go on to the next edge. This edge is now p, or the next road coming out of city 3. All right, so we ask ourselves, is this city number 4 in the tree already? It is not, which is good news. So we continue to ask whether this weight is less than this best distance that or best cost that we have seen so far for getting to city number 4. We haven't seen any ways of getting to city number 4 yet. This is less than max or infinity. So then we say the best way of getting to city number 4 is in fact from city number 3, and we can do it at a cost of $10 million. That's, again, these two lines of code right here. And then we have now processed all of the edges out of city number 3, which means we are going to move into the next phase of the algorithm, where again we set v equal to 1 just arbitrarily and kind of blindly, saying like the best city to build to next is blindly city number 1. Of course, we're going to discover that it's not that. And we set distance, or dist, equal to max, and again this represents the minimum cost we have seen so far for building to a new city out of all of the cities that we could possibly build to. Okay, so we begin our for loop, which again is over here. We are going to iterate from I equals 1 up to the number of cities, or the number of vertices in the graph. We first check whether this vertex is in the graph already. It's in the graph already, so we don't have to consider this one as a possible next vertex to go to. We ask ourselves, is this vertex in the graph already? And it is not. So then we ask ourselves, is it cheaper to get to this than the best city we have seen so far? Or the cheapest road to a new city that we have seen so far? And the answer is, well, we haven't seen any roads to new cities so far from our current set. So yes, this is our best option, and we update dist, and we update v to be 2, which means city number 2 is currently winning for best city to visit next, or to build to next. Okay, we increment I to 3, but this city is already in the tree of accessible cities. We've already built a road to it, so we don't have to worry about that one. And then we check city number 4, is it in the tree? No, it's not in the tree, so it's a possible next city to build to. And is it cheaper to build to this city than it is to build to the cheapest city we've seen so far? And the answer is yes, it is cheaper. So we update our dist variable. The cheapest city we have seen to build to so far now costs us $10 million to get to. And we update our v to say that the best city to build to next is city number 4. And now we've iterated through all of the different cities, so our for loop terminates, and we move right into the next while loop, iteration of the while loop, and set in tree for city 4 to be true, which means we have chosen essentially to build this road. But again, I don't mark that anywhere directly in the code, so I won't color code it. I just note that the parent of city 4 is city number 3, and I can get from city 3 to city 4 at a cost of $10 million, like along this edge, along this road. Okay, and so then from here, we start to move a little bit quickly. We process the edges out of 4. We see that there is an edge from 4 to 2. Is this edge cheaper? Well, first of all, 2 is not already in the tree, and then we ask ourselves, is this edge or is this road cheaper than the cheapest road we've seen so far to city 2? And the answer is yes, so we update the cheapest road we've seen so far to city 2. And we also update the parent. That is, we can now get to city 2 from city 4 at a cost of $5 million. We are now done processing this edge. We go to the next one, this $10 million edge, but this points back to a city that's already in the tree, so we skip right over that one. And we are done processing the edges out of city number 4. We move to the next phase of the algorithm where we blindly set v equal to 1 and dist equal to max. That again means that in this iteration of the for loop that we're about to do, where we iterate through all the cities, the cheapest road that we've seen that we can build to a new city kind of costs an infinite amount of money because we haven't seen any roads. We haven't started our for loop yet, so we haven't actually seen any roads that build to new cities. All right, and now we start our for loop. We say I equals 1. This points to a city that is already in the tree, so we skip it. This points to a tree that is to a city that is not in the tree, and the cheapest road that we can build to this city costs $5 million, which is less than infinity. So we update dist to be 5, and we update v to be 2, meaning that the best city we've seen so far to build to next is city number 2. All right, we keep going with our for loop. We increment I to 3, but index city number 3 is already in the tree, so we skip over it. We go to city number 4, which is already in the tree also, so we skip over that. And so the best city to build to next is indeed city number 2, which means that our for loop terminates. We move right into the next while loop. We set in tree for city 2 equal to true, and we consider all of its edges. Or all of the roads that come out from it. Now, you might say at this point, like, we don't have to do this, right? Because we've already marked, like, we've already gotten to all the cities, right? But I'm just executing the algorithm as it's written. The algorithm doesn't know that we're done yet. And it turns out it doesn't take too much extra time for the algorithm to just keep, do this iteration like this whole while loop one more time. If we wanted to be super, super careful about our runtime here, we might try to come up with a different way of keeping track of when the algorithm finishes. But for now, for purposes of keeping the code simple, we just run through the whole while loop again. And so we check all the edges from city number 2, but all of these edges point to cities that have already been, that are already in the set of accessible cities that are already in the tree, right? And then we move to the next phase of the algorithm where we blindly set v to 1 and distance equal to max, and then we run through our for loop here. And it turns out when we run through this for loop, all of these guys are already in the tree, which means that we don't process any of them. And then why does our algorithm terminate? Our algorithm terminates because we never reset v to be anything other than 1. Remember when we blindly set v to be 1? And 1 is already in the tree. So at the end of this for loop, our v, which is 1, is already going to be in the tree, which means when we go back to the beginning of this while loop and check the condition of the while loop that says in tree for v equals false, well, that's not going to work and our algorithm's going to be done, right? Okay, so now our algorithm terminates, and the question is, how would we reconstruct the tree using the information we have in these variables? Well, the first thing that we're going to do is look for the vertex that's going to be our root. And how will we recognize the vertex that is our root? It will be the root of our family tree because its parent is -1. That is, it doesn't have any parent. It's kind of our great-grandma of the tree. And that root is vertex 1. Okay, and then we say to ourselves, okay, how do I know where to go next? Well, I look for any children of vertex 1. That is, I look for any vertices, I iterate through all the vertices, which I'm not going to do with actual code, and check to see whether any of them have 1 as a parent. And it turns out that vertex 3 has 1 as a parent. So then vertex 3 is going to be a child of vertex 1 in the tree. And then I iterate through the remaining vertices 2 and 4 to see whether either of them have 3 as a parent. And lo and behold, 4 has 3 as a parent, so 4 is a child of 3. And then I iterate through the only remaining vertex, which is 2, to see whether its parent is 4, and it is. So therefore, 2 is a child of 4 in the tree. Okay, great. So that's a complete run through with the code. And now you might be kind of wondering, well, what would happen if I had a different tree besides like this example, right? And in particular, if you're familiar with depth first and breadth first search and so forth, you might be thinking to yourself like, well, is it like depth first search or breadth first search where I'm basically like, after I search one vertex, I just go to another vertex and then I look at the edges that come out from that vertex, and the next vertex that I'm going to go to is always going to be connected by a road from exactly the previous vertex that I'm coming from. That's been the case in at every point in the algorithm as we have run it so far. And the answer is no. It does not have to be the case that the city that I'm going to build to next is going to be directly connected to the city that I built to most recently. That does not have to be the case. And we will run through a quick execution of the algorithm on a different graph that shows that that doesn't have to be the case. Okay, so here's our new graph. We have 5 cities this time, 1, 2, 3, 4, 5, with roads that cost 10 million, 30 million, 50 million, 60 million, and 80 million respectively. And we are going to choose this time to start at city number 3. Okay, so v equals 3 is our choice, and we immediately mark city number 3 as being in the tree, and its distance as being equal to 0. And then from here, we have to process its edges. We have to look at both of the roads that come out of city number 3 and figure out which is cheaper. The $30 million road points over to city number 2, which means we can get to city number 2 from city number 3 for $30 million. We look at the other edge out from city number 3. It costs $50 million, and that means we can get to city number 4 from city number 3 for $50 million. And then we are going to arbitrarily again set v equal to 1, just like we did last time. That's part of the code. We always just arbitrarily start with the first vertex. And dist equals max, which means during the current kind of iteration of the for loop, or execution of the for loop, the cheapest road that we have seen to a new city costs infinitely many dollars because we haven't seen any of them yet, right? So we set dist equal to max, and then we set I equals 1, and we start looking through all of our cities for the cheapest one to build to next. So we do that. This has infinite distance away from our current set of accessible cities because there are no roads we have seen yet to city 1 from our set of accessible cities, so we don't update anything there. But here, when we go to city number 2, we do update the dist variable because 30 is cheaper than infinity. And then we also set v equal to 2. Our best option is currently 2. And then number 3 is already in the tree, so we skip over it. City number 4 has a distance of 50 away from our current set of accessible cities. That is, it would cost $50 million to build to vertex 4, which is not cheaper than our best current option of $30 million. So we don't update anything here. We go to number 5, and number 5 is not even accessible. It costs maximum amount of money to get to number 5, so our best option is number 2, which means we mark 2 as being in the tree, and then we look at the edges or the roads out from city number 2. We check this road over to city number 1. City number 1 has not yet been accessible, so the cheapest way to access city number 1 is to use this $10 million edge from city number 2, and we update those guys. And then we check the other road out from city number 2, but that points back to a city that's already accessible, city number 3, so we don't worry about that. We run through the for loop and set things appropriately. Now city number 1 is in fact accessible at a cost of $10 million. Cost of $10 million. So dist is 10 with vertex 1. 2 has already been discovered, so we don't worry about that. 3 has also already been discovered. And 4 has not been discovered, so we now ask ourselves, what would it cost to get to vertex number 4, which is quite far from vertex number 1? And the answer is $50 million, or excuse me, from vertex number 2. It's quite far from vertex number 2. And the answer is it's $50 million, which is not cheaper than the best option we've seen so far. So we skip over that, and 5 is still not accessible, so we skip over that. And city number 1 wins, and we build to city number 1 next. City number 1 is now in the tree. We check its out edges. First, this one points back to city number 2. We do nothing there. And then this road points over to city number 5. So the cheapest way of getting to city number 5 is now from city number 1 at a cost of $80 million. And we are done processing the roads out from city number 1. We move on to the next phase. We set dist equal to max, and we start our for loop, etc. And here is where it gets a little bit interesting. Up until this point, we have always been choosing the next city to be some city that is directly adjacent to the most recent city that we added, right? So number 1 is the most recent city that we added. Number 5 is the only city we haven't gone to yet that is adjacent to city number 1. So if we were kind of following our previous pattern, we would like only go to city number 5, right? But we're actually going to iterate through all of the vertices. 1, 2, 3, 4, and see that 4 is accessible not from city 1, but from some other city in the set of accessible cities, namely city number 3. And so we are going to set our dist variable to 50, indicating that the cheapest road that we can build to a previously unaccessed city costs us $50 million, and that road goes to city number 4. And then we check city number 5 to see whether it's cheaper, but it's not. It's $80 million, which means the next city that we are going to build to is actually city number 4, which is not adjacent to the most recent city that we built to previously, city number 1, right? So we are always considering all of the possible cities and not just the ones that are adjacent to the most recent city we added. Okay, so from here, we finish the algorithm. City 4 is set to be in the tree. We check its edges and so forth. I'm going to run through this very quickly. We note that, in fact, it is cheaper to get to city number 5 from city number 4 than it was from city number 1. And so the distance is 60, and the parent is now 4 instead of 1. We are done with the edges. We move to the next phase. We iterate through the for loop here. And when we get to city number 5, we discover that's our best city to go to next. Oops, this should have read 60 instead of 50. That's a slight error on my part, but we are going to city number 5 next. We go to city number 5. Now city number 5 is in the tree. Technically, we run through the last iteration of this while loop, and that takes us to the end of the algorithm. I'm going to skip over that last iteration of the whole while loop. Okay, so the algorithm is now finished, and that concludes our basic run through of Prim's algorithm here. But for further study, if you're interested, it should be noted that Prim's algorithm can be implemented more efficiently using a priority queue to track the next vertex to be added to the tree. So the way that we had been doing that is by using this for loop and iterating through all n vertices or all n cities in our graph. So that means basically that this for loop is going to run, like there are going to be n iterations within this for loop every time this for loop happens. And furthermore, this while loop overall is going to run n times, where n again is the number of cities or the number of vertices in the graph. And so whenever that happens, n executions of the while loop, each of which contains n iterations of some for loop, the runtime is going to be quadratic for our algorithm. Using big O notation, we would say that the runtime of the algorithm is O of n squared, which is not particularly fast. And there is a faster way to do it. If we use a priority queue instead of this for loop at the end of the algorithm here, we would start inserting edges into a priority queue, which takes, it turns out, log of n time. And we can do this whole Prim's algorithm in like an O of n log n kind of time if we use a priority queue. If you're interested in that, you can look it up for further study. That's all.